Hello, so in this video we're going to start talking about this thing called a difference equation. Now if you remember in the last video, we pulled up this. So in other words, in the last video we basically had a situation where we either started at 0 or we moved left. So basically, we started at 0, then we could either move left or right with each time step. So we could either move here or we could move here, and then from here we could either move here or we can move here, or we can move here or we can move here. So basically, we started building it up into kind of, like this, and we ended up coming up with a distribution or PDF that kind of defined this, and it was normally distributed, as we said. So we basically kind of considered it as almost like a glide. But the trouble is with that. The trouble is with that in the last video was that it doesn't take into account for bias. So for example, if you start here, and you can either move to here or here. Well, this might correspond to, say, food. This might correspond to food, and this might correspond to no food. So therefore, obviously, the animal that starts here is more likely to move left. So therefore, it's it becomes biased. Well, what we had before couldn't deal with stuff like that. Or otherwise, it may be the case that the animal kind of stays there, so it doesn't have to move. In the previous example, we had to move. So we had to either move left or we had to either move right. But we didn't really consider the case, well, okay, what happens if we stay where we are? Okay, you couldn't do that in the last model. So now what we're doing now with this thing called difference equations is to basically take into account for that. So to take into account bias, so for example, moving one way over the other, and waiting time. So for example, just staying exactly where we are. Okay, so now this is what we're going to do with this example. Okay. So the idea is that with each time step, which we're going to call tau, we move a distance. We move a distance, which is delta. So this is time step. This is time step, and this is distance that we move for each time step, delta. Okay, and either we move to the left, okay, which we're going to call L, fairly obviously, okay, or we move to the right. We move to the right, and we're going to call that, guess what, R. Yeah, or we don't move, Now, what is it if we don't move? Well, we know the total probability the total probability of the system should add up to 1. So in other words, the probability of moving left plus the probability of moving right times plus the probability that we don't move. Let's just call it, A for the time being, because we don't know what it is, or D or whatever. Don't move. Let's just call it DM. Okay, so don't move. Okay, so plus probability that we don't move. Okay, that must all add up to 1. So therefore, what is, the probability that we don't move? Well, if we just take these two things over to the other side, so in other words, we end up with, take those two things over to the other side. So therefore that becomes minus. So therefore it's going to become minus L minus R. So in other words, the probability that we don't move then is 1 minus L minus R. Okay, so that is now what we don't move, right? So these are the three things that we now need to consider. So if we move left, we call that L. If we move right, we call that R. And if we don't move, we call that 1 minus L minus R. Okay? Now it's important to note that L, whereas before, we could either move left and we could either move right, and we kind of considered, because we're moving an equal time step each time, moving left is exactly the same as moving right, because we're moving an equal time step. But now L may not always be equal to R. It could be equal to R, but it may not necessarily be equal to R. And so therefore, what this is saying is that, if we start at 0 and we move to the right, or we move to the left, what this is basically saying is that we could move, or we could be more biased to be moving, or more likely to be moving in one direction than the other. So, for example, moving to the left, we're more likely to move to the left or move to the right. So, therefore, this is what's known as bias. Okay, so we're more likely to move to the left than we are to move to the right. Okay, so if say, L was bigger than R, yeah, so we're more likely to move to the left. Okay. However, the total probability of the three events must still always add up to 1. So these things must always still add up to 1. Okay. So okay, the way which we're going to go about this is sort of ever so slightly different. Okay. So basically, we're going to say we know where we are at t plus tau. So in other words, at t plus tau, we're going to say we know we're at this position here. Let's call it x. So we know at t plus tau that we are at this position x. Okay. Well, where were we? What we're going to now ask. So in other words, we start somewhere and we move by one. We move by a time step. So in other words, this is post movement. We've already done the movement and we know where we are. And the questions which we're now going to ask is, well, where could we have been previously? Whereas before, again, this is another difference between what we had before. Before, we kind of said, right, this is where we start. We start at some position. We start at some position here. We can either move right or we can move left from that position. Now what we're going to do is go about it in a slightly different way and say, actually, we know where we're going to end up. So where were we previously? Okay? Well, let's have a think. Well, we know that we've moved by some time step delta, or we moved by some distance delta. So we could have been over here on the right, which is obviously going to be at x plus delta, because we're going to have to move, if we move to the left, say, so we started here, and then we move to the left, okay, well then we're moving by a distance of delta, so, we would have been at x plus delta. Yeah. Equally, we could have been over here. And we could have moved to the right by a distance of delta. So therefore, we would have been at x minus delta. Okay. Or we could have just been at the same position as we are now, because of course, not moving is equally a possibility. So, where could we have been? Not at t, but let's have a look at tau. Where could we have been? Well, we could have been at x minus delta. Okay, or we could have been at x plus delta, or we could have just been exactly where we are, because of course we didn't have to move. Okay, so these are the three positions that we can be at. We can either be here, or we can be here, or we can be here. So at t, we're here. At t plus tau, we end up at x. That's all we know, right? So let's consider, first of all, if we started here. First of all. Okay, so therefore, and we end up at x, so therefore we're moving right. Okay, so basically what the probability is, we're moving from x minus delta, okay, in some, at t, this is where we start, t, because of course t is just n times my time step, okay, so the number of steps I've taken, times by my time steps, so t times by moving right, okay, because obviously I'm moving right. Okay, so that's if I started here. Now let's consider the case if I started over here. Let's consider the case which I started over here. So that's scenario 1, right? So scenario two is if I started over here on the right and I move left, because of course I have to end up at x. So I move left. So therefore that's the probability that I start at x plus delta. Okay, given some time steps at t, times by moving left, because of course we're moving from here to here, so we're moving left. Okay, so that's scenario 2. Well, scenario three is if I started here. Scenario 3 is that I started here. Scenario 3, so I started here. So therefore, the probability that I start at x, okay, in some time, okay, times by the probability that I don't move. Well, the probability I don't move, I just define by 1 minus L minus R. 1 minus L minus R. So this is going to be 1 minus L minus R, okay, times by that. Well, I know that the total probability must add up to 1. So I know at t plus tau, I end up at x. So therefore, the probability that I end up at x at t plus tau, so after my time step, after my movement, is just some probability density function, okay, times by, so it's just going to be these three things added together effectively. So it's going to be what's it going to be? It's going to be the probability of x minus delta t times r. So I'll just write it as r, that's fine, plus this second one, so p of x plus delta t times l, okay, plus this is an l, that's quite a nasty l, there we go, plus this last one, so probability of xt times by 1 minus l minus r. Okay, so now this is, if you like, my probability density function. Okay, so this is actually, well, it's not. It's a difference equation. This is now my difference equation. Okay, equation. Now this is exact. because it only gives it only gives in terms of what we were previously. So whereas before we were considering, we start somewhere and we consider where we can go. Now what we're doing is we're considering where we are now and where we were previously. So everything, if you like, is known. So therefore, this is exact, right? This is an exact thing because we know where, we have the possibilities of where we were previously. Okay. Now we can actually work with this. We can work with this thing, and we can work with it by using something called the Taylor series. Now we have kind of looked very briefly at Taylor series before, and we've actually looked at the case where we've got two variables. But I'll just write out the sort of single variable case and then kind of compare the two. I'm not going to go into details about where everything comes from. I'm just going to give it to you, and hopefully you can see kind of just by looking at the single variable case that f of a plus some distance h is given by f of a plus h times the derivative of my function evaluated at a plus h squared over 2 factorial, okay, times f double dash of a, and then plus, we just tend to write all the terms after that as just something called O, which is higher order terms, okay, and the higher order terms in this case will be all of the terms which are above h cubed, because we've expanded up to h squared. So therefore all the higher order terms, they're just like everything, because of course this is an infinite series, okay, this will carry on forever and ever and ever, but I just tend to write all of those terms that continue after that point as this, okay, so everything after h cubed, okay, so that just stands for higher order terms. Okay, it's just a very quick kind of reminder of what's going on. Now notice that h is just a really, really small value. H is just a really small value. Effectively, this is just my Taylor series of a, just with some really tiny value added, and I'm talking sort of fractions. Okay, so if we square a fraction, if we cube a fraction, or raise a fraction to a power 4, raise a fraction to a power 7, 8, 9, 10, we raise a fraction to bigger and bigger values. So, for example, a half to the power of 10. Okay, well that's going to be 1 over, I think that's 1024, I think that's right. Well, that's tiny compared to a half squared, which is obviously a quarter. Well, that is obviously bigger than that. So basically, as we raise, h is just a really, really small value. I'm talking a fraction. Okay, so therefore, as we raise it to a higher and higher power, all of these terms are just going to become negligible. Okay, so that's just the reason why I can kind of condense them into higher order terms. Okay, that's all that's going on there. So let's try and now do the same thing. I'm just going to write out all of my Taylor expansions for this thing, and for this thing here, because of course we know what that is there. So let's have a look for the Taylor expansion of P of x t plus tau. Okay, I'm not going to go into y because this is technically of two variables, which kind of I can't remember whether we've done in this course or not, but you can do it. Okay, you just end up with partial differential equations. I think I have done a video on this. I'm not sure whether it's in this course or where is it, but I know I have done a video on it. So hunt around. It's probably called Taylor series. And I know it's one in ordinary differential equations, certainly. So have a quick look at that if you need to. So this is just the probabilities. This is just my function. So I'm expanding around my point xt. So if you like, this is a bit like my function at my point. Okay, plus my small perturbation term. A small term which I'm adding on in this case is tau. So it's going to be tau. Times by the partial derivative, so it's just going to be my derivative of my function around my point, so derivative of my function around my point, xt, over, what am I differentiating with respect to? I'm differentiating with respect to t, because that's what's in there, that's what I'm adding my perturbation term to, or my small little term, which I'm adding to, that is t, okay, and then I've just got sort of higher order terms. I'm just going to sum all the terms after that. And of course, it's going to be everything above t squared. Okay, so I'm not going to bother expanding all of that out. Okay, notice that it's partial derivative now because, of course, I've got two variables involved. I've got two variables involved in my function, so I have to choose which variable I differentiate with respect to. But basically, I'm just kind of oversimplifying, if you like, because I can. Okay, so now let's expand out for p of x minus delta. So where's x minus delta? So I'm going to expand out for that one. X minus delta, and then I'm going to do the same for x plus delta in just a moment. So I've done that one, so now I'm going to try and expand that one out. So p of x minus delta. So p of x minus delta, t, okay, I'm expanding around xt, is going to be p of xt like I had before. It's just my function evaluated at my point. So it's like my function, if you like, is just my probability. It's my p. Just treat it as a function, okay? P of xt. Then I'm going to end up with a minus term. I'm going to minus term because, of course, I'm using minus delta. Whereas before I'd be using plus h, which is why there's a plus h there. Now and likewise here I'm using plus tau, which is why the plus tau there. Okay, now all I'm doing is I'm using minus delta, so therefore there should be a minus delta there. Minus delta there. So my delta's a bit dodgy. Times by the derivative, so I've got the derivative of my function. Now this is going to get a bit awkward because I've got deltas and dels going on, which look kind of the same, but I'll try and differentiate them. Deltas is my time step. Delta is my partial derivative. So, you know, with delta going that way, with the tail going to the right is my delta, okay, but tail going to the left is my partial derivative, okay. So delta p around my point xt, so if you like the derivative of my function around my point xt, over, and I'm differentiating now with respect to x, because of course x is what's being added. You know, I'm adding my differentiation, adding my small little term, my small little delta to x now, whereas before I was adding my small little term to t, so that's why I differentiated with respect to t. Okay, now what I'm doing is I'm adding my small little term to x, which is why I'm now differentiating with respect to x. Okay, and I'm just going to expand one more term out again, and if I expand another term out, it's going to be delta squared, which is y now, because it's going to be minus delta squared, which is going to become a positive delta squared, over 2 factorial, so it's over 2, times by my second derivative of my function. Second derivative of my function around xt, so this is, you know, I'm evaluating this bit now, around xt, over the second derivative of my function, differentiate with respect to x. Okay, and I'm just going to have some higher order terms which involve delta. Okay, and it's going to be everything above delta cubed. Okay, similar kind of thing now, but I'm going to do it so I've done that one and that one. I'm going to do it now for p of x plus t. So let's do this. So p of x plus delta, p of x plus delta, okay, around t. Same thing again, it's just going to be the value of my function. Okay, it's going to be the value of my function. So value of my function around xt, so value of my function around xt. Okay, my perturbation term is plus delta, so that's my plus h, if you like, times by my derivative of my function with respect to x. So that's that bit there taken care of. So my next term then is my second derivative of my function, second derivative of delta over 2, times by the second derivative of my function. I'm doing the same thing again. Second derivative of my function around xt with respect to x squared. Okay, and then I'm just going to have again plus higher order terms on the end. So plus higher order terms, and they're going to be involving delta cubed. Okay, so now this is all my expansion for each of my different functions. So here we have, you know, I've just derived them all. I've just written them out neat. So there we are, nice and neatly. This is just what we've just derived. Okay, so now what the idea is that we want to now plug these three things into the thing which we just got above, so this thing. So we want to plug it into this thing here. So basically we want to put, where are we? We want to put that into there, okay? We want to put this into there, okay? And likewise we want to put that into there. Okay, so that's basically the idea behind what we're going to do now. And just for neatness' sake, I'm going to drop, whenever I see a p of x of t, I'm just going to call that p, okay? Because I'm just going to basically drop the dependence on x and t, just because it makes things so much easier and so much nicer to work with. Okay, so much easier and so much nicer to work with. Because if you notice that, you know, this thing, I can replace it so that it only has p of x and t in there. Okay. Also, as well, it might be a useful thing to note out here. Notice that I've only expanded that up to the kind of, you know, the first order of tau, whereas I expanded, you know, these two things here up to, you know, my second order. So the reason for that will come clear later, because I'm going to take a limit effectively, and the reason for that will come clear. But for the moment, just don't worry about it. I just have done it. Okay. So okay, first things first, I'm going to replace this by this. So in other words, you know, that will go in there. So what do I end up with? Well, I get p plus tau lots of dp by dt, plus some higher order terms that I'm not really that interested in, not really that worried about. Okay, but I'm just going to keep them in for the moment. So I've replaced that thing there by this thing here. So next job then is to set, I've got P times 1 minus L minus R, 1 minus L minus R. That's fine. Okay, so keep that there, and then I'll just replace that thing, and I'll just got to remember multiply it by my R. By where are we? By this thing in the middle here. So I'm going to replace it by all of that thing there. Okay, so plus P minus delta del P by del X plus delta squared over a 2 times the second derivative of P with respect to X squared. Plus then some higher order terms involving delta cubed. Okay, then finally, all I'm just going to do, I've got to multiply all that by R, so what do we end up with? That thing, okay, should all be multiplied by R, okay, and then finally, I'm just going to replace that thing there, by what are we replacing it with? Replacing it with that thing in there. Okay, so let's see if I can fit this in. So plus, okay, P plus delta lots of dP by dx plus delta squared over 2. This is much harder to write than you think. So I've got to remember to, sometimes which way the tails go. So delta squared over P over del x squared plus some higher order terms involving delta x cubed or delta cubed times by what am I multiplying by? I'm multiplying by L. Okay, so let me just write this out a little bit neatly. Okay, so there we are, just written out sort of a little bit more neatly now. There's a few things that I can do with this before I do anything else. Okay, first of all, I can note I've got a higher order term involving tau squared there. I've got a higher order term involving delta cubed there, and a higher order term involving delta cubed there. So in other words, I can combine all my higher order terms just kind of together at the end. So in other words, the fact that this is being multiplied by R and the fact this is being multiplied, the fact this is being multiplied by R and this is being multiplied by L, I'm not worried about. Okay, so just get rid of this. I can just basically take this out and take this out. Okay, it's not going to make a blind bit of difference, and just write it together in one term. Because I've got two higher order terms involving delta cubed at the end. And likewise, I'm going to take this over here as well. The fact that it's going to become a minus, again, I'm not worried about it. It will all be taken care of. It's a bit like, when you're adding constants to things, you can just kind of write them all together as one big constant, because it will all be taken care of automatically. So this is tau squared. Okay, so these are all my higher order terms now. So let me just write this a little bit more compact. So there we go, that's exactly the same thing, I've just got rid of all the gaps. Okay, so what can I do with this now? Okay, well let's try and expand the brackets then. So let's first of all deal with this first term. So let's multiply through by P here. So we end up with P times 1, which is just P, minus P times L, which is just PL, PL, minus P times R, Okay, so that's what I end up at the beginning there. Now let's multiply through by R, this whole second thing through by R. So I end up with, what do I end up with? I end up with RP, okay, minus R times this thing, so R delta, plus, let's try and move this over, plus R times that thing. So R delta squared over 2 times by second derivative. Same thing again for L, so just multiply through by L, so I end up with LP, LP plus L times delta plus L times delta squared over 2 times that thing. Okay, and therefore, I'm not worried about these things for the moment. I'll just leave them hanging around at the end. Okay, so let's have a look and see what we've got. Well, look, I've got a PL here and a PL here. Okay, so those two things will cancel off. And I've got a PR here and a PR here. So those two things will cancel off. So I've got automatically a cancellation. Are there any other cancellations that will happen? Well, yes, look what happens here. If I take this P over to the other side, so let's write this P over here, so minus P, I've got a plus P and a minus P. Those two things cancel. So what am I left with? Let's just get rid of everything that cancels. So what am I left with? That cancels and that cancels. So what am I left with? I'm effectively left with this. It makes it a lot smaller. So let's have a look at this. So there we are, that automatically looks a lot smaller. So what can I now do with this? Well, let's have a look. I've got a dP by dx here, and I've got a dP by dx here. Likewise, I've got a d2p by dx squared here, and a d2p by dx squared here. So can you guess what I'm going to do? I'm going to do a bit of factorising. So first of all, I'm going to factor out, what I'm going to do, if I just write this down below actually, just to write this out again, and then I'll just try and work with it, okay? So there we are. Okay, I've written this exact same thing as I've got here down below. The only thing that I have done is I've just swapped these two terms in the middle round. So, you can see that I've just swapped those two terms in the middle round. It's exactly the same thing because I'm adding. Okay, so I am allowed to do that. I've just basically written them the other way round. Okay, just makes it kind of easier to see what I'm going to do now. So the idea is that, you can see here, actually, I can take out a little bit more. I've got a delta times delta p over dx. And then I've got a delta dp by dx here. So I can just expand that out. So I can just write it as, if I just expand that out, so in other words, if I expand this out, I'll just be left with an L minus R. L minus R in the middle. Yeah, an L minus R, because I've got a minus R here, we've got an L here, so I'll just be left with L minus R when I expand that out. Okay, and likewise here, if I take out, look what I've got common to both, I've got delta squared over 2 times by d2p by dx squared in both of these. So therefore, if I expand this out, I will just be left with an L plus R. So let's try and write this out properly. So I'll just be left with an L plus R. So there's plus there, L plus R in the middle there. Okay, plus sort of my higher order term. So, already that looks a lot neater. Okay, but actually I can do a lot better than that. Okay, so if I just make a substitution, so if I just say, okay, let's say epsilon is just going to correspond to L minus R. Actually, I'm going to be a little bit more sneaky here. Here where I've got L minus R, I'm just going to take out a minus in front of there. Now, you may think that's strange. Why am I taking a minus out? So I've got R minus L in there. Why am I taking a minus out? What I had before looked far neater. I didn't have a minus here. The reason why is because then we can write it in a far more meaningful way. In other words, we can kind of see what's going on in a lot more detail, kind of what we end up with. We can interpret much easier, basically, in the next video. Okay, so, that's the reason why I'm just doing that. So what I'm just going to do is I'm just going to let epsilon equal this R minus L. I'm going to let epsilon equal this R minus L. Okay, and I'm going to let kappa, which I'm going to write like that, and I'm going to let that equal the L plus R, So, in other words, I can now replace this with epsilon. I can now replace this by epsilon, and I'm actually going to write this with the delta, so just rewrite it, it's just multiplication. I can write it in any order, right? And this I'm going to replace by kappa. Just going to replace by kappa, but of course I can write this with this. Okay, so in other words I get this times by kappa. Oops, just squeeze that over a touch. There we go. This is over to kappa over 2. Okay, so this is effectively what I'm left with now. Okay, and of course I've still got a tau here. So in other words, if I divide through by tau, so let's just divide through by tau. So this is over tau. And this is over tau, so in other words, I put tau down there. Then therefore, this is what I'm left with. Okay, so I'm left with this, so some constant, effectively, plus that, and then I'm left with that thing in the middle. I'm just left with that, plus some higher order terms. Oh, and don't forget that I've also got to do a little bit of replacement in here rather. Because I've got to divide through by tau, also in these higher order terms as well. So I've got to divide through by tau and divide through by tau. So what am I left with in here? This is going to be delta cubed over tau, and this thing is just going to be tau because it's tau squared over tau, which is just going to become tau. Okay, cool. So, okay, well let's just have a thought. Let's just have a think about what we want to do now. Well, basically we want to make delta go to 0, so we want to make our time steps go to 0. Okay, so the distance that we travel, we want to make that go to 0. So we also want to make our time steps go to 0 as well. Okay, but notice as well, we also now want to make epsilon go to 0 because the distance between right and left, okay, so this is left and this is right, so left and right, we want to make that overall distance as small as possible. So therefore, we can also say as well, the epsilon we want to make go to 0 as well. We want to make now epsilon go to 0 as well. Okay, so this is what we've got. So therefore, if we let u be the limit, of, what do we want? We want u to be the limit of this coefficient here. So delta, epsilon, and tau. Okay, and if we make these three things go to 0, and epsilon, if we make those three things go to 0, then we're going to call that u. So basically, as we make those things get smaller and smaller and smaller, we're just going to say, well, it's just going to approach some value. right? If we make those three things get smaller and smaller and smaller, effectively all we're just doing is we're just making these two time steps get smaller and smaller and smaller, and that value we're just going to call u. So basically, just make it smaller and smaller. We're going to call that time step u. Okay. So we're going to u equal, u equal that thing. Okay, and we're also going to let d. We're also going to let d equal equal this thing here, so this coefficient here. So we'll let d equal this coefficient here, okay? So it's going to be the limit as of delta squared times kappa over 2 tau, okay? And we're going to make, well, we know we want to make delta and tau go to 0, right? We know we want to make delta and tau go to 0. But what about kappa? Well, kappa is defined as L plus R. So we don't want to make... that wouldn't be that useful to go to 0 as such. So all we're just going to do is we're going to actually just take a kappa out the front. Okay, just going to take a kappa out the front. I mean, I could have taken, I suppose, that epsilon out the front if you didn't quite see, if that made things a little bit more confusing to you. But, let's just take a kappa out the front. Why not? Okay. So therefore, it's going to approach some value t and that d, and that's called a diffusion coefficient. But notice as well what's going to happen with our higher order terms as we make delta and tau go to 0. Well, what's going to happen to this thing? What's going to happen to this thing as we make tau go to 0? Well, that's just going to go to 0 ordinarily, because this is going to become a higher order term involving terms which are 0, right? It's going to become higher order terms involving 0. So that's going to go to 0 automatically. That's quite easy. What about my other one? So my delta cubed over tau. What's going to happen as we make that go to 0? Well, no, actually, we don't want to make that go to 0. We want to make that go to, what do we want it to make go to? We want to make it go to r times d, yeah? Okay, and that does make it go to 0 anyway, but we want to make it go to r times d, and that will automatically make it go to 0. Okay, don't worry too much about that. So basically, what we're left with is if we let u equal that thing in there. So as we go to 0, we get u equal to that thing there, let d equal to that thing there, and these two things will both go to 0. What we're left with? Well, we're left with the derivative of p with respect to t, so that thing, that's what we're left with still. That's what we're left with. Okay, and we've replaced that by u, so that's equal to minus u times the derivative of p with respect to x. Okay, and we replace d by this thing there, so we've got plus d times the second derivative of p with respect to x. Okay, and then the higher order terms go to 0. So effectively, this is what we're left with. Now, notice, I mean, this may not be that useful to you guys, but notice that if we let epsilon actually equal to 0, so what was epsilon, remember? Epsilon was r minus L. So in other words, what we're saying is that if r equals L, so in other words, we're moving equal distance either side. Okay, so we've got our time steps. We start at 0, we move in equal distance left or right. So r equals, the distance we move to the left is the same as the distance we move to the right. Okay, so they're same, so r equals L, then therefore epsilon must equal 0. So if epsilon equals 0 in this, then u must also equal 0, because this then becomes just 0, so it's just going to be the limit of 0, so therefore u must go to 0. So therefore, what do we end up with? If r equals L, then we end up with this, just of interest. We end up with this. This term effectively just disappears, right? This effectively just disappears, so we're just left with plus d times the second derivative of p with respect to x. Okay, and this is actually something known as the diffusion. This is something called the diffusion equation, or the heat equation in partial differentiation or partial derivatives. Okay, it's useful. Basically, what we're saying is that because diffusion and heat is kind of the whole idea is that if you heat up the end of the rod, then we can use this equation to model how the heat will move through the rod. Okay, it's exactly the same kind of thing here. It's sometimes called the heat equation or diffusion equation, because diffusion is how things move over time. Okay, so if we're basically saying that it can move in either direction in kind of equal amounts in either direction, then therefore we can pull out the diffusion equation from it. So that's kind of useful to people that are into differential equations. But otherwise, this is the general form. So the derivative of p is equal to minus u times the first derivative of p with respect to x plus the second d times the second derivative of p with respect to x. Okay,